In last video lecture, we discussed about the heat of reaction or enthalpy of reaction and dependence of enthalpy of reaction on temperature, that is the Kirchhoff's equation. That is at the end of video we got one equation, Kirchhoff's equation, that is delta H2 minus delta H1, that is equal to delta Cp into T2 minus T1. Now next point is, or next term, that is standard heat of formation, delta HF0. Now the enthalpy change that accompanies a chemical reaction in which 1 mole of pure compound, it is formed from the elements in their standard states, it is called standard enthalpy of formation. Simple definition of standard heat of formation is, it is the amount of heat evolved or absorbed when 1 mole of pure compound is formed from the elements in their standard states. That heat, it may be formed, it may be evolved or absorbed. That heat, it is called as standard heat of formation. Now here, what is the meaning of elements in standard states? Elements in standard state means the pure elements like pure oxygen, pure chlorine, pure sodium, pure magnesium metal. These are the elements in their standard states. Enthalpy of all the pure elements in their standard state, it is considered as 0. For example, suppose you consider the formation of hydrochloric acid, HCl, hydrogen chloride. Now hydrogen chloride, it is considered to be formed from pure hydrogen and pure chlorine. These are the elements in standard states. So half mole of hydrogen reacts with half mole of chlorine gas, and there is a formation of 1 mole of chlorine. Hydrogen chloride, 1 mole of hydrogen chloride. So at the time of formation of 1 mole of hydrogen chloride from these elements in standard states, there is a liberation of or evolution of 22 kilocalorie of energy, and this is the enthalpy of formation of hydrogen chloride. Consider another example. Consider the formation of acetylene, C2H2. This acetylene, it is formed from or considered to be formed from pure carbon and hydrogen. It means 2 moles of carbon reacts with 1 mole of hydrogen. There is a formation of 1 mole of acetylene. There should be 1 mole of product always. And at the time of formation of 1 mole of acetylene, whatever enthalpy change, that is the heat of formation of acetylene. Here, at the time of formation of 1 mole of acetylene, there is an absorption of 53 kilocalorie of heat, and therefore heat of formation of acetylene, it is 53 kilocalorie. So heat may be evolved or absorbed. This is very important. During formation of compound, heat may be evolved or absorbed. Now already I told you the standard enthalpy of formation of elements in their standard state is 0, and the elements in standard states, these are maybe pure hydrogen, chlorine, oxygen, okay, and their enthalpy is considered as, enthalpy of formation is considered as 0. Now from enthalpy of formation, we can find out the heat of reaction or standard heat of reaction. So standard heat of reaction, it is equal to standard enthalpy of formation of products minus standard enthalpy of formation of reactants. So standard heat of reaction, this can be calculated from standard enthalpy of formation of products and reactants. Now next term is standard heat of combustion. Standard heat of combustion. Now combustion means burning of compound in excess of oxygen or air. This is called as combustion. During combustion process, there is oxidation of any organic compound or any substance, and for oxidation there is a need of oxygen, and therefore the standard heat of combustion, it is the enthalpy change that accompanies a reaction in which 1 mole of compound is completely burnt in excess of oxygen. It is called standard enthalpy of combustion. In short or briefly, we say that heat of combustion means the amount of heat liberated or evolved when 1 mole of compound is completely burnt in excess of oxygen. It is called as heat of or standard heat of combustion. For example, when 1 mole of carbon is completely burnt in excess of oxygen, there is a formation of carbon dioxide, and at the time of burning of 1 mole of carbon, there is a evolution of 394 kilojoule of heat. So minus sign indicates that heat is evolved. Actually, this 394 kilojoule heat, it is evolved at the time of burning of carbon. So this is the enthalpy of combustion of carbon. At the same time, in another way we say this is the enthalpy of formation of carbon dioxide also. Actually, enthalpy of formation of carbon dioxide, it is reverse of the enthalpy of or this is enthalpy of formation of carbon dioxide. This is nothing but the enthalpy of combustion of 1 mole of carbon. Both the values are same, that is delta Hc, that is delta H means heat of combustion of carbon, it is equal to minus 394 kilojoule. Another example, when 1 mole of methane is completely burnt in excess of oxygen, we get carbon dioxide and water, and at the time of burning of 1 mole of methane, there is a liberation of or evolution of 88 kilojoule of heat, and this is the enthalpy of combustion of methane. Enthalpy of combustion of methane. So the standard enthalpy of combustion of any compound, it is always negative. Heat is always evolved at the time of combustion of substance. So it is always negative. What are the applications of heat of combustion? So first application is we can find out the heat of formation of compound. Already I told you heat of formation, it is reverse of heat of combustion, and therefore just by changing the sign we can get the heat of formation. So from heat of combustion we can find out the heat of formation. Another application is to calculate calorific value of food and fuel. What is calorific value? The amount of heat produced or liberated in calories when 1 gram of substance means fuel or food, is completely burnt in excess of oxygen. That is called as calorific value, and from heat of combustion we can find out the calorific value. And third important application is from heat of combustion it is possible to know the constitution of organic compound. In organic compound, how many carbon atoms are present? This can be obtained from heat of combustion. You know that in homologous series, actually in homologous series of organic compound, each neighboring member differ by means of CH2 unit. That is called as homologous series. For example, when we consider the homologous series of alkane, then methane, ethane, propane, butane. Now in between or two neighboring members differ by means of CH2 group. So this is what is homologous series. So here in homologous series, the difference between heat of combustion of successive member, it is nearly constant and it is equal to 158 calories. What it means? Suppose there is a methane, ethane, propane, butane. So heat of difference between heat of combustion of methane and ethane, it is 158 calories, or difference between heat of combustion of ethane and propane, it is also nearly constant, that is 158 calories, or this much heat or energy difference, it corresponds to the CH2 group. And using this principle, we can find out the carbon chain length in the organic compound. So just by knowing the heat of combustion, it is possible to know the constitution in organic compound. So these are the applications of heat of combustion. Now next important term, that is the bond energy or bond enthalpy. Now bond energy means the average amount of energy required to break all the covalent bonds in 1 mole of substance to form gaseous atoms or radicals. It is called as bond energy or bond enthalpy. So bond enthalpy, it is always positive and it is expressed in or measured in kilocalorie per mole or kilojoule per mole. Now most important thing is, what is the definition of bond energy? The average amount of energy required to break all the covalent bonds in 1 mole of substance to form gaseous atom or radicals. This is called as bond energy or bond enthalpy. To break any particular bond, energy is required and therefore it is positive. Okay, so this bond enthalpy or bond energy, it is a measure of strength of bond. Greater the strength, greater is the bond energy, and vice versa. So just by knowing bond energy or bond enthalpy, it is possible to know about the strength of that particular covalent bond. Now again, important thing is, for diatomic molecule, bond enthalpy, it is equal to the enthalpy of atomization, whereas for polyatomic molecule, average bond enthalpy is considered. In case of polyatomic molecule, the average bond enthalpy of particular bond is always considered. So this can be clear by some examples. Suppose hydrogen, it is a H2, it is a diatomic molecule. When it dissociates, there is a, after atomization, we get 2 hydrogen atoms, and whatever enthalpy is required, that is the bond dissociation energy or enthalpy of atomization, and that is nothing but the enthalpy of or bond enthalpy of hydrogen, and it is equal to 436 kilojoule. Similarly, for chlorine, bond enthalpy is 242.7 kilojoule. For HCl, to break bond, energy required, it is 431.9. But water is a polyatomic molecule. Bond breaking takes place in 2 steps. In first step, energy required is 499 kilojoule. In second step, energy required, it will be 428 kilojoule. But the actual bond enthalpy, it is the average of these 2 values. So when the sum of these 2 values is 927, and when we take average of these 2, 927 by 2, it is equal to 463.5 kilojoule, and therefore average bond enthalpy for OH bond in water, it is 463.5 kilojoule. It means for diatomic molecule, enthalpy of atomization, it is nothing but bond enthalpy. but for polyatomic molecule average bond enthalpy is considered.